Hello grade 12 students, welcome to this video. In this video we're going to do some exercises of chapter 9, function of neuron. So let's move to exercise 2. Exercise 2, to study the properties of a neuron. The setup schematized in document 1 realized, and a giant axon of a squid is used. Here we have two stimulating electrodes, EE1 and EE2. And we have ER1, which is a recording electrode, and ER2, which is reference electrode, and here they are connected to an oscilloscope. So the scanning is set to a slow speed and at a time t0. ER1 is introduced into the axon. Electric stimulations of increasing intensity from S1 to S5 are applied at different times from T1 to T5. So at T1, S1, T2, S2, and so on. And the graph is in document 2 is obtained. This graph, when both electrodes at time EAB, here at point B, here introduction of ER1 in the axon. So A to B, both electrodes, they are placed on the surface of the axon. So there is no action potential AB. This means that there is no potential difference at the surface of the axon. So here we don't have an action potential on the surface of the axon. When ER1 is introduced inside the axon tracing BC, a potential difference was obtained and it's equal to minus 70 millivolts. So this means that the interior of the axon is more negatively charged compared to the exterior, and the difference is equal to minus 70 millivolt. Due to the absence of stimulation, tracing BC correspond to the resting potential. We don't have any stimulation, so this is the resting potential BC. This is port A. Port B, referring to the recordings obtained due to the stimulation S1 to S5. What can you deduce concerning the property of the axon of the squid? So when we did stimulation of increasing intensity, S1 and S2, S1 and S2, there is no action potential. This indicates that these two stimulations, they are ineffective. They are below the threshold of excitation. While after the stimulation of intensity S3, the action potential is recorded for the first time. This means that S3 is called the threshold of excitation. S4 and S5, so as we increase the intensity of the stimulus beyond S3, above S3, S4, and S5, we get the constant maximum amplitude of 100 millivolt from minus 70 to plus 30. So it's 100 millivolt. This indicates that S4 and S5, they are called effective stimulation. So here we can deduce that the axon of the squid is excitable and it follows or it obeys the law of all or none. Either we have an action potential here or we don't have in S1 and S2. For intensities equal or above the threshold of excitation, the response is always of the same and of the constant amplitude. So the amplitude is constant, is always maximum. While ER1 is still inserted in the axon, and to better analyze the recording obtained by stimulation S5, the scanning speed is increased. The tracing is in document 3 is obtained. So here in document 3 we obtained the tracing of the scanning speed is increased, the tracing is observed, the potential difference, and document 3. Part C, they said, identify the different phases of this graph by specifying the corresponding ionic phenomena. Okay, we have to say that the graph of document Z is corresponding to the action potential obtained after applying a stimulation. So first, you have to say that curve AB, this is the time needed for the nerve impulse to reach the recording electrode. So it represents the time needed or the time delay. while BC, it corresponds to the depolarization. So the time of this from 0.75 to 1 is 0.25 second AB. Okay, so the time of AB is 0.25 second from 0.75 to 1. BC, it corresponds to the depolarization. Depolarization from minus 70 to about to 45 approximately. So this is approximately 45. So this is called depolarization. So from minus 70 to 45, minus 70 plus 45, it's about 115 millivolt. So during this phase, what happened? The sodium voltage dependent channels, they open and they allow the inflow of sodium ions. So more positive charges will be deposited on the inside of the axon. This will make it more electropositive. Moving to the phase which is CD. CD corresponds to the phase of free polarization, going back to the polarization, going back to the minus 15 millivolt. During this phase, what will happen? The sodium voltage dependent channel, they close, and the potassium, they open. So an outflow of potassium will occur. Thus, the intracellular medium will become more electronegative. That's why we have the repolarization. Moving to the last one, DE, the phase DE. Here we go back to the repolarization more than the polarization is called hyper-polarization. It drops below the resting potential. This is hyper-polarization by less than minus 10 millivolt. So there is a small outflow of potassium where the potassium ion, they are closing but slowly. Thus, the electronegativity inside of the axon increases, so increasing more than the resting potential, so it drops less than the resting potential. This is part C. Okay, guys? Let's move now to exercise 4. The motor neuron represented in document 1, this is the motor neuron M, is found in the spinal cord. It indicates the nervous messages coming from many sources to assure a coordinated response of effector organs. It's in contact with terminal buds of sensory receptors or of interneurons. So in order to register the activity of this motor neuron, a recording microelectrode is inserted into its cell body and shown in document 1. And a number of effective simulations, they are applied. These simulations, the results are obtained, and the recording of these simulations obtained in documents 2 and 3. Let's start first specifying the type of the synapses in each case to justify your answer. So first of all, we have the synapse between the neuron A and the motor neuron. Neuron A and motor neuron, which type of stimulation is applied? The stimulation S1. So let's look to the recording of S1. Here it's the S1. S1, it showed a hyperpolarization, meaning that the synapse between neuron A and the motor neuron is an inhibitory one. So since after applying a stimulation S1, it showed a hyperpolarization from minus 70 to approximately minus 72. So this first one is an inhibitory one. This is as inhibitory. Moving to the second synapse. The synapse between neuron C and the motor neuron upon stimulation of S2. So upon stimulation of S2, we have tracing B. So we have an action potential obtained. We have hypopolarization from minus 70 about minus 67 millivolt approximately. So this means that this is an excitatory synapse. This one is an excitatory one. While the synapse between neuron B and the motor neuron, after applying neuron B and the motor neuron M, is an excitatory one. Why? Because since tracing of document 3, obtained, it shows hypopolarization from minus 70 to about minus 60 approximately. So this one is S3. So this S3, it's between the neuron B and the motor neuron M. Okay, so here we have 2 excitatory till now and 1 as inhibitory. Okay, let's move now to the synapse between neuron A and the motor neuron M. Neuron A and the motor neuron M, already we said that it's an inhibitory one, so it shows a hyperpolarization, and hyperpolarization is shown here between the neuron A and the motor neuron M, and the synapse between neuron D and the neuron B. Let's see here, neuron D and the neuron B. So after applying both S4 and S3 together, S4 and S3 together, as you see here, S4 and S3, both of them, they are applied. We have here a decrease in the action potential. So we have a hyperpolarization from -70. This one was decreased since the synapse between neuron D and neuron B is an inhibitory one. Why? Because since the tracing B, this tracing of document 3, it shows that after we did stimulations S3 and S4 together, it shows hyperpolarization from -70 to -65 approximately. So -70 to -65 due to the effect of these two stimuli. This amplitude is smaller than S3 alone. So S4 has decreased. It has an inhibitory role and the effect of the neuron B on the motor neuron. So this is the result here. Let's move now to the precursor of labeled neurotransmitters. Precursors of labeled neurotransmitter with radioactive isotope are injected in the terminal buds. This allows us to follow the path of neurotransmitters at the activation of synapses by studying audio radiographs. So document 4 gives results obtained after labeling of two neurotransmitters, acetylcholine and gamma aminobutyric acid, which is called GABA. So plus means presence of radioactivity, minus absence of radioactivity, and two pluses, we have high quantity of radioactivity. So let's start first with the first result. In effective simulation S3, radioactivity of M1 shows high amount or high quantity of radioactivity, while radioactivity of M2 shows null, absence of radioactivity. S4, then S3, we have small or presence of radioactivity, while the absence in document 1 of N and M2. So in S3, we don't have radioactivity absence in both. So S4, then S3, we have absence of radioactivity of M1, absence, and we have high amount of radioactivity of M2. These are after the injection of labeled precursor of acetylcholine, and the second one was after the injection of labeled precursors of GABA. So upon the simulation S3, following the injection of radioactive acetylcholine into the synapse, radioactive acetylcholine appears in high quantity where? In M1, only in M1 and not in M2. And they are present in less quantity when S4 and S3 they are applied together. You see the difference here? They are present in high amount when applied alone, and in a normal quantity or normal amount when S4 and S3. So acetylcholine is the neurotransmitter where in M1. While after the stimulation S3, following the injection of radioactive gamma aminobutyric acid GABA, so in the synapse there is no radioactive GABA appears. So after applying the S3 then S4, so radioactive GABA is detected in high quantity in M2. So GABA here is the neurotransmitter in M2. Okay guys? Moving to the last part, suggest an explanation for the mode of action of neuron D on B. So neuron D has an inhibitory role. Neuron D has an inhibitory role on neuron B. Why? Since the stimulation carried by S4 then by S3 causes the decrease in the effect of B on M by decreasing the exocytosis of the neurotransmitter. In the case of acetylcholine M1. So the nervous message transmitted by D and by S4 causes exocytosis of GABA from the terminal buds of neuron D. So GABA will bind to the receptors on the membrane of neuron B, causing hyperpolarization, which is known by IPSP, inhibitory postsynaptic potential. This hyperpolarization in neuron B prevents neuron B from reaching its depolarization threshold. This arrival of the message leads to the exocytosis of lower quantity of acetylcholine, which produces an EPSP of smaller amplitude. Okay? So exercise 2 is talking about when both electrodes are placed on the surface of the axon, there is no potential at AB. This may be explained by the fact there is no potential difference at the surface of the axon. Same charges, they are detected by both electrodes. When ER1 was introduced into the axon, the phase BC, there is a potential difference that's equal to minus 70 millivolt recorded between the interior and the exterior of the axon. As such, the interior is more electronegative, or it's more negatively charged than the exterior, and the difference in the potential is equal to minus 70 millivolt. Due to the absence of stimulation, tracing BC correspond to the resting potential. Moving to part B, upon stimulating the axon by stimuli of intensities S1 and S2, no action potential is recorded. This indicates that S1 and S2, they are ineffective, below the threshold of excitation. Upon stimulation by stimulus of intensity S3, the first action potential of amplitude 100 millivolt is recorded. So this indicates that S3 is the minimum effective stimulation. This is called the threshold of excitation. As the intensity of light stimuli increases beyond S3, we move to S4 and S5. An action potential of the same constant and the maximum amplitude, which is 100 millivolt, is recorded. What does this indicate? This indicates that S4 and S5, they are effective stimuli. From all this, we can deduce that the axon of the squid is excitable and it obeys or follows the law of all or none. Either we have an action potential or we don't. So it doesn't respond to stimuli of intensities below the threshold of excitation. For intensity equal to or above the threshold, the response is always of the same constant and maximum amplitude. The graph of document C corresponds to the action potential obtained directly after applying an effective stimulus at t equal 0.75 millisecond. Curve AB correspond to the time delay, the time needed for the nerve impulse to reach the recording electrode, and it's equal to 0.25 millisecond, from 0.75 seconds to 1 second, where the recorded potential is the resting potential, minus 70 millivolt. Curve BC corresponds to depolarization of plus 115 millivolt from minus 70 millivolt to 45 millivolt. During this phase, sodium voltage dependent channels, they open and they allow the inflow of sodium ions, so more positive charges will deposit on the inside of the axon, making it more electropositive. Here the potassium channels, they are still closed. Curve CD correspond to the repolarization phase of 115 millivolt. During this phase, sodium voltage dependent channels, they close right now. In the repolarization, they close, and potassium voltage dependent channels, they open. So an outflow of potassium occurs, thus the intracellular medium becomes more electronegative. Curve DE corresponds to the hyperpolarization of minus 10 millivolt. During this phase, there is a slight outflow of the potassium ions, where these ions, where the potassium channels, they are closing, but slowly. Thus electronegativity on the inside of the axon increases more than the resting potential. So let's move to the solution of exercise 4. As we said, the synapse between neuron A and motor neuron M is an inhibitory synapse. Since tracing of document 2 shows upon stimulation S1 a hyperpolarization from minus 70 to minus 72 millivolt. Also, the synapse between neuron C and motor neuron M is an excitatory synapse. Why? Since tracing B of document 2 obtained upon stimulation S2 shows a hyperpolarization from minus 70 to minus 67 millivolt. The synapse between, here we have hyperpolarization. The synapse between neuron B and the motor neuron M is an excitatory synapse. Why? So here we have inhibitory, we have hyper, excitatory hypo, and there's one excitatory hyperpolarization from minus 70 to 60 milli. The synapse between neuron A and motor neuron M is an inhibitory synapse. This is the tracing, inhibitory 1. This is the tracing of document 2 obtained shows a hyperpolarization from minus 70 to minus 72 millivolt. The synapse between neuron D and that of neuron B, it's an inhibitory synapse, since the tracing of B of document 3 shows upon 2 stimulation S3 and S4 a hyperpolarization from minus 70 to minus 65 due to the effect of 2 stimuli. This amplitude is smaller than S3 alone, so S4 has decreased, or it has inhibited the effect of neuron B on motor neuron. So upon stimulation S3, following the injection of the radioactive acetylcholine into the synapse, radioactive acetylcholine appears in high quantity in M1 only, and present in low quantity when S3 and S4 they are applied. As such, acetylcholine is the neurotransmitter where in M1. While after applying a stimulation S3 following the injection of radioactive gamma aminobutyric acid into the synapse, no radioactive gamma appears. So upon applying S3 then S4, GABA is deducted in high quantity only in M2. As such, GABA is the neurotransmitter where in M2. Part 4, last part, neuron D has an attenuating or a modulating or an inhibitory effect on neuron B. Since the stimulation carried by S4 then by S3 causes a decrease in the effect of B on M by decreasing the exocytosis of what? Exocytosis of acetylcholine. Okay, so we have decrease in the exocytosis of acetylcholine. The nervous message transmitted by D causes the exocytosis of GABA from the terminal buds of neuron D. GABA will bind to its receptors on the membrane of neuron B, causing hyperpolarization IPSP. This hyperpolarization in neuron B prevents neuron B from reaching its depolarization threshold, or the threshold of depolarization. The same, so the arrival of the nervous message at 3 leads to the exocytosis of lower quantity of acetylcholine, which produces EPSP, but with a smaller or less in amplitude in motor neuron M.